Hey, Honors Chemistry, it's good to see you. It is April 3rd, Friday. Let's turn to page 516 and start section 2. 516, section 2. Now, it says in here that the greatest majority of chemical reactions are exothermic. What that means is heat is released. And as heat is released, the material is coming into a more stable configuration, a lower energy state. Now, in endothermic reactions, you put energy in order to keep it going. And so as a result, the products are less stable. But however, some endothermic reactions can occur spontaneously. You see, with an exothermic, you put a little heat in to activate it, and it can run by itself. Think of a log that's burning. Once you get it initiated, it just continues to burn and goes on by itself toward the products. That's called spontaneous. Endothermic, you have to put energy in. If you quit putting energy in, it'll stop. In order to drive it forward, you got to add energy. But there are some that are spontaneously simply because they're falling into pieces. For example, let's take a look at the decomposition of ammonium nitrate. You can see a picture of it on page 517 on that test tube being heated up. Ammonium nitrate looks like this. Ammonium nitrate, solid. We're decomposing it. And it says it falls into nitrogen, water, and oxygen. And so we're going to balance this thing, and we're going to end up with 2241. I'm not going to spend time working out the balance. Instead, I'm going to tell you what these products are. This is gas. This is liquid. That's gas. This is solid. So you can see that a stable compound is becoming unstable products. Why? Because you have more gaseous things and a liquid thing as compared to a solid thing, which is crystalline in nature. It goes like this. Solid, liquid, more freedom of motion, a little bit more randomness, and then gases, boom, all the bonds of attraction are broken, and there's entire randomness. Randomness is called entropy. And on page 517, entropy, capital S is the symbol, can be defined as in a simple qualitative way as a measure of the degree of randomness of the particles in a system. So here's what happens in nature. Processes in nature tend to flow tend to head toward cooling off and falling apart. And slowing down, you might say, because of frictional forces. Slowing down. Cooling off. And falling apart. Falling apart is greater randomness. And so we're going to call that greater entropy. Cooling off is loss of heat. Cooling down in temperature would be lower enthalpy. And slowing down would be simply because of, as I suggested, frictional forces and things like that. So what am I telling you? I'm telling you processes in nature are cooling off and falling apart and slowing down. Like a top, it's going to fall over. It's like your bedroom. If it's not maintained, it's going to just fall apart on you. Okay, and so energy is only one half of the picture in terms of whether an equation is going to drive toward the products. You also have to consider entropy, enthalpy and entropy. Take a look on page 518. The classic illustration of entropy change, greater entropy, would be like ice that is melting. All right, so where does the heat go? The heat goes into tearing the ice apart and making it more random. Okay, and then, so that's a change of state. And also dissolution. So if you take salt or sugar and you put it in water, the water acts like, as I've already talked to you about, the dissolution process pulls it apart, breaks down that crystal, that grain, and turns it into formula units, as in the case of salt, or molecules in the case of sugar, and tucks those pieces of formula units called ions in between the water molecules, or molecules of sugar in between the water molecules. And so as a result, you get a more random situation. It isn't as orderly as it is in a grain crystalline structure. It is now dissolved. So changes of state produce a greater randomness, and the changes in dissolution creates more randomness. Changes of state, of course, from solid to liquid, or from liquid to gas, is what I'm talking about, greater entropy. Now look on the middle of page 518 with me. Free energy changes determine if a reaction is endothermic or exothermic. Underneath that, it says processes in nature are driven in two directions, toward less enthalpy and towards greatest entropy. And I've already discussed that with you. When these two oppose each other, the dominant factor determines the direction of change. And so we have what's called the Gibbs free energy, and that is an equation that looks like this. Gibbs free energy equation looks like this. Delta G, change in Gibbs free energy at standard states, 1 atmosphere, 25 degrees Celsius, is equal to the change in enthalpy. We've been learning about that in the last section, minus T delta S. And that's standard conditions as well. And you can see that on page 518. This is temperature in kelvins. And this is change in entropy. And this is change in enthalpy. And so this is temperature. So this quantity has two factors involved, temperature and entropy. And this is enthalpy. And enthalpy is joules per mole, or kilojoules per mole. And this is degrees Kelvin, or Kelvin, no, there's no degree on it, times kilojoules per mole. And so it's called kilojoules per mole Kelvin. And so the Kelvin temp cancels, and you have kilojoules per mole minus kilojoules per mole. And so this would be in kilojoules per mole. Tomorrow, which is Monday. Tomorrow, I'm going to start talking to you more about Gibbs free energy and how that can be used as a predictor of whether or not you're going to have a spontaneous equation or not, whether or not it's going to continue to drive toward products on its own. And we're going to look at the bottom of page 519 at a table to determine that. I'll give you some problems to work out. It'll be back to math again. And so this is Friday, and I'll see you.